Hi there, my name is Nadia El Gamal. I'm the lead author of a technical publication titled The Design, Construction, and Thermodynamic Analysis of a Direct Expansion Solar Assisted Heat Pump for Cold Climates. I'm happy to be virtually presenting on behalf of my group today for IMECE 2022 International Mechanical Engineering Conference and Exposition. Over the last year, I've had the pleasure of working on this research paper with 5 of my colleagues whom, along with myself, were all undergraduate students in the final year of our mechanical engineering degree. The project itself was completed under the supervision and guidance of 2 faculty members in the Department of Mechanical and Manufacturing Engineering at the University of Calgary. We are also very fortunate to have received external sponsorship from Emerson, who supplied all of the necessary HVAC components for the development of our prototype, as well as served as our main point of contact for validating and troubleshooting our engineering design, and quite frankly, without whom this technical submission would not have materialized. So a great thanks to Joshua Bowles at Emerson for all of his help. Our team has also been extremely lucky to become connected with local consultants in Calgary, including Class Mechanical and Chinook Refrigeration, who've graciously assisted us with the assembly of the prototype and have been very generous in providing their technical insights along the way. Now, last but not least, a final special thanks to FN Insulation as well for sponsoring the mineral wool needed for the completion of the prototype. So our research focus was designing a direct expansion solar-assisted heat pump that could satisfy the domestic hot water heat load demand of the average Canadian household. We've placed a lot of emphasis on designing the technology for cold climates because the research with regards to the feasibility and operability of these systems in these cold weather conditions is somewhat lean and for, obvious or fair reasons. Deploying new technologies of this sort in climates of high precipitation and a low count of bright sunshine hours is challenging from both a technical and a financial standpoint. And so the validation of this technology within these locales has not been conclusive in any sense. Wanting to contribute to the ongoing research on the technology, we decided to design, fabricate, and test the prototype in Calgary, which, as you may know, is one of the sunniest North American cities, receiving over 2,300 bright sunlight hours a year, making it the perfect location wherein to test and validate our prototype. Now, without delving into the statistics on global greenhouse gas emissions, which are readily available for anybody really to read on the internet, I'd like to emphasize that although this technology presents a clever engineering solution, the true motivation behind exploring this technology is that there needs to be a shift in the current energy landscape and an investment in cleaner technologies. Now, as I've mentioned earlier, for our research, we focused on implementing the system for the provision of domestic hot water for the average Canadian household. And you may wonder why. The reason is that domestic hot water heating is among the highest energy depleters in the building sector and accounts for about 20% of the residential energy usage in Canada. And so with decarbonizing water heating, we can significantly reduce emissions of greenhouse gases into the atmosphere. Now, let's talk about the technology itself. On the screen here is a simplified diagram of the thermodynamic cycle and the key system components. As you can see, the system is comprised of 4 primary components, namely an evaporating unit, which is comprised of a solar thermal collector, a compressor, a complete condensing unit, which is comprised of a coaxial condensing coil, a water pump, as well as an insulated recirculation water tank, and finally, to complete the cycle, an electronic expansion valve. Now, the cycle begins when solar energy in the form of radiation is captured by the absorber plate and converted to heat. The working fluid, or refrigerant, which flows through multiple small pipes attached to the back of the absorber plate, heats up and is subsequently causing its enthalpy value to increase. Following compression by the compressor we have here, the refrigerant flows into the coaxial condensing coil, and this is really where the magic happens. So as you might imagine, within the condensing coil, the refrigerant, which is at a higher temperature than the pumped domestic water, rejects its heat to it, rendering it ready for domestic use. Now, to continue the cycle, the now cooled refrigerant is depressurized via an electronic expansion valve and flows back to the solar thermal collector, where it can experience more useful heat gain and repeat the cycle. So to meet our design heat load, the first step was actually sizing our solar thermal collector to determine the useful heat gain we can actually extract from it. And to quantify the heat gain, it was first important to characterize an overall heat loss coefficient such that we as designers wouldn't minimize solar energy gains by undersizing our flat plate collector or maximize losses due to oversizing it. It was all a balancing act, and so it was only fitting to conduct an energy balance on the plate as seen in the diagram. Now, as shown on here, some of the incident solar rays on the flat plate collector is immediately lost due to reflection off of both the flat plate collector as well as the glazing material. Additionally, both the flat plate collector and the glazing material experience convective and radiative heat losses to the environment due to being at a higher temperature. Now, these are all the main modes of heat losses in the flat plate collector and can collectively be known as top losses. Okay, so our biggest challenge was quantifying these top losses, and the reason is that the empirical solution to determining the overall heat loss coefficient and subsequently the useful heat gain relied on knowing the absorber plate's mean temperature. And so, the only reasonable approach was for us to develop an iterative solution to our system of equations on MATLAB. The code itself extracted the thermodynamic properties of our refrigerant from the CoolProp library and allowed us to iteratively solve the Hotel-Willier equations. The converged solution, although not really a transient state analysis, provided an estimate of the performance of the design system in terms of the theoretical useful heat gain of the collector, as well as the theoretical coefficient of performance, or COP, of the entire heat pump cycle, which in layman's terms simply means how well our system would be at moving heat from one location to a more useful one. Now, to keep this video short and sweet, you can find the entire algorithm and justification behind it detailed in the technical publication once it is released by ASME. Knowing this key information about our cycle, however, we were able to move on to the second phase of our design process, which was component selection. Let's take a closer look at our solar thermal collector. The entire assembly was modeled on SolidWorks and consists of an aluminum absorber plate painted with a black silicone-based selective coating that improves the aluminum's absorption of the incident solar radiation and maximizes its ability to retain the heat. The custom manifold running below the absorber plate consists of 5/16 of an inch sealed copper standard coils. The piping manifold was screwed into the aluminum absorber plate, and the presence of air gaps between the piping and the plate was eliminated through the application of a specialized heat transfer paste into the crevices. On top of the absorber plate is the glazing, which is a low iron tempered glass of high optical clarity that allows the vast majority of incident solar rays to pass through. The bottom and sides of the assembly were insulated using mineral wool to prevent further heat losses to the environment. Finally, the entire assembly was encased using pine wood and a plywood backboard. When modeling this design, we accounted for important design considerations such as thermal expansions and constrictions in the grooves holding the absorber plate and the glazing, as well as deflection of the glazing and the aluminum plate materials, and that was essentially to help us determine the appropriate depth for the casing that would both accommodate the deflection as well as allow for sufficient air gap so as to not stunt the performance of the insulating material. The manifold design, specifically the diameters of the copper tubing as well as the pitch distances between each loop, were determined by performing a parametric study of these variables and ensuring our ultimate selections would yield the best possible performance. So after a conducive component matching exercise to ensure that our chosen HVAC components would indeed satisfy the heat loads we set out to achieve, we moved on to the fabrication and assembly phase of our design process. A big aspect of this was developing a custom support frame for what ended up being a 2.3 square meter size solar thermal collector weighing a whopping 150 pounds or even over. And one of the most important design considerations we focused on was fabricating a frame that would be disassemblable and can be easily transported to and from the testing site, which would ideally be the roof of a building, and can also be stored easily. And since we couldn't source such a frame for a reasonable price point, we decided to expand our scope of work to design and fabricate a 3-part welded steel frame with telescoping joints for ease of disassembly. During the design, we also conducted fitment dimensioning to ensure that the assembly can be accommodated by standard facility doors and freight elevators once it is completed. Now here's a little close-up of the team working hard to MIG weld the steel frame, and you can also see the telescoping joints and the final support frame with casters installed for ease of hauling. So another important design aspect of the custom manifold was the actual custom manifold that holds the refrigerant beneath the aluminum absorber plate. And since we did not have access to bending tools that were large enough for us to achieve the radius of curvature of the manifold, we decided to hand bend the 5/16 inch sealed copper using a die. We then screwed the copper manifold beneath the aluminum absorber plate, and to eliminate any air gaps that would compromise heat transfer from the plate to the manifold, we applied a specialized heat transfer paste to ensure that the manifold would be flush with the absorber plate. For the final assembly, we contracted Chinook Refrigeration and Air Conditioning professionals to braze our manifold to the external piping network that connects the solar thermal collector to the rest of the refrigeration and water side cycles. Their licensed technicians were also able to assist us with charging the prototype with our chosen refrigerant, as well as conduct a leak and pressure testing of our prototype. Now, to validate our theoretical results, we designed and instrumented our own data acquisition system using an Arduino microcontroller as well as temperature and pressure sensors. Now, put simply, knowing the specific enthalpy of our refrigerant at certain points, which are labeled on this figure, would allow us to determine the COP of the system. The specific enthalpy, which is H in this equation, can be determined easily from property tables at measured temperature and pressure values. As such, temperature sensors at 3 locations, so at locations 1, 2, and 3 on this diagram, as well as pressure sensors at 2 locations, 1 and 2, or the suction and discharge of the compressor, were used to extract this data. So here you can see the data acquisition system that is actually implemented in the prototype, and how it works is that it has to be turned on when the system is turned on at the start of the day. Then it records measurements every 30 minutes. And to do this, we added a micro SD card and an SD card module so that the Arduino can write the data onto the card. The Arduino doesn't do accurate timekeeping, so a real-time clock module was also added. And when the Arduino isn't connected to a laptop, we have a 5-volt USB battery power supply for it that just plugs into it. The thermistors, on the other hand, operate at that power as well, but for the pressure transducers, an external power supply was needed. So preliminary testing of the direct expansion solar assisted heat pump system was conducted on June 27th of this year, and the results are tabulated in the technical publication, so if you're interested, I encourage you to read it. As for now, additional testing is underway to fully characterize the system and troubleshoot arising difficulties, but from the results we've seen and presented, we believe this technology is very promising and has the potential to be widely implemented in the near to mid-future in Canada. Now, thank you very much for tuning in, and we look forward to presenting our findings on this topic in person during the International Mechanical Engineering Exposition and Conference in Ohio this November. Thank you.